Good morning all. Myself Jafrunisa from Government College for Men, Karnool. In this session, I am going to discuss what is meant by Lagrange's theorem and what are the basic definitions we need to understand this theorem. First, we will see the statement of this theorem. The order of subgroup of a finite group divides the order of the group. So this is the statement of the Lagrange's theorem. To understand this theorem, we should know few basic definitions like group, subgroup, order, coset, index, and finally we will prove the Lagrange's theorem. First, we will discuss the definition group. An algebraic structure G circle is said to be a group if it satisfies the following properties. Here the algebraic structure is nothing but any non-empty set equipped with the binary operation. Here G is the non-empty set and circle is the binary operation. Her first law or property is closure law. Closure law states that if you take any two elements in the set G, then a circle B is also belongs to the same set G. For example, if you take the set of integers, then if you take any two integers minus 2 and minus 3, if you add minus 2 and minus 3, we will get minus 5. Minus 5 is also an integer. Hence, we can say that plus satisfies the closure law in the set of integers. And next law is associative law. It states that if you take any three elements in the set A, B, C belongs to G, then A circle B, circle C is same as A circle, B circle, C. Third one is identity law. It states that if you take any element A belongs to G, then there exists another element E belongs to the same set G such that A circle E is equal to E circle A is equal to A. For example, if you take any integer minus 4, then there exists another element 0 belongs to the same integer set such that minus 4 plus 0 is equal to 0 plus minus 4 is equal to minus 4. Here 0 is called as the additive identity. Similarly, in case of multiplication, 1 will be the multiplicative identity because 4 into 1 is equal to 1 into 4 is equal to 4. And next property is inverse law. Inverse law states that if you take any element A belongs to the set, then there exists another element B belongs to the same set such that A circle B is same as B circle A and both are equal to E. E is nothing but identity element. So here as an example, if you take 4 in the set of integers, then 4 minus 4 is equal to minus 4 plus 4 is equal to 0. So here minus 4 is called as the additive inverse of 4. Next we will see subgroup. So subgroup is nothing but first of all it is a subset of the group. We take G be a group and H is a non-empty subset of G such that H dot is a group. That means if H satisfies all the properties of the group, then we say that H is a subgroup of G. Next, order of the group, where it is very simple. The number of elements in the group is called as the order of the group. It is denoted by order of G. For example, if you take G is equal to 1 minus 1 I minus I, it is a group with respect to the multiplication. Here order of G is equal to 4 because G contains 4 elements. In the second example, if you see G is equal to Z plus, it is also a group. Set of integers with respect to the addition is a group because it satisfies all the 4 properties. It is a group and the number of elements in the Z are infinite. So order of G is equal to infinite. Next we will see what is meant by finite group. If the number of elements in the group is finite, then we say that it is a finite group. Otherwise, it is said to be an infinite group. In the above example, we can easily see that the first example, G is equal to 1 minus 1 I minus I is a finite group, whereas the second example, G is equal to Z plus is an infinite group. And the next important definitions are coset and index. So first we will see what is meant by coset. So here let H dot is a subgroup of group G dot. So here we are considering one subgroup Let A belongs to G. A is any element in the group G. Then the set A into H is equal to AH such that H belongs to H. It is called as the left coset of H generated by A. Similarly, the set H into A is equal to HA such that H belongs to H. It is called as the right coset of H generated by A. So here depends upon the position of A. If A lies on the left side, then we say that it is a left coset. If A lies on the right side, we say that it is a right coset. And next one is index of subgroup of a finite group. H be a subgroup of a finite group G, then the number of distinct left or right cosets of H in G is called the index of H in G. To understand these two definitions in detail, let us consider one example. So first we will take one group G is equal to 1 minus 1 I minus I with respect to the multiplication. And the subgroup H is equal to 1 minus 1. It is a subgroup because it satisfies all the properties of the group and it is a subset of G. Right. Now, right cosets of H or right cosets means H into 1. So here 1 is the element in the group G and it lies on the right hand side. So hence it is a right coset. So H into 1, it can be obtained by multiplying the each element of H with 1. 1 into 1 minus 1 into 1. So 1 comma minus 1. This is one right coset. And next right coset H into minus 1. And H into I. H into minus I. So if you observe all these four cosets, you can observe first two are same. 1 minus 1 is same as minus 1 comma 1. And I comma minus I is same as minus I comma I. Right. Here the number of distinct right cosets are 2. So this is the way how to write the right cosets here. And actually there are 4 right cosets. Out of 4, 2 are same. So distinct, that means different right cosets are only 2. So here index is nothing but the number of distinct left or right cosets is called as the index. Here in this example, we can find only 2 distinct right cosets. They are 1 minus 1 and I minus I. These two are the distinct, hence the index is 2. And one more thing you can observe, and if you take any 2 left or right cosets, they are either disjoint or identical. So if you observe 1 minus 1 minus 1 1, these two are identical. Similarly, if you observe 1 minus 1 I minus I, these two are disjoint. No single element is common in these 2 right cosets. So either any 2 left or right cosets are either disjoint or identical. So keeping all these points in view, now we will prove the Lagrange's theorem and we will observe the statement once again. The order of subgroup of a finite group divides the order of group. Here we have to remember one point. Lagrange's theorem is applicable only for finite groups. So to prove this theorem, first of all we will take one finite group G and H is the, obviously H will be a finite subgroup of group G. So here first case, if H is equal to G, so subgroup is same as the group G, then obviously order of H divides order of G. If the number of elements in group and subgroup are same, 4 divides 4, 6 divides 6, like that, order of H divides order of G. So there is nothing to prove this theorem. Now we will take the second case. What is the second case? H is not equals to Z. So if H is not equals to G, that means the number of elements in the group G is different as the number of elements in the subgroup. Let order of G is equal to N, means G contains N number of elements and H contains M number of elements. Now we have to prove that order of H divides order of G or M divides N. Here we know that every right coset of H in G has same number of elements and the number of right cosets of H in G is finite. To understand this statement, let us consider this example given in the box. So already we have discussed this one. G 1 minus 1 I minus I, H is equal to 1 minus 1. Here we have written all the right cosets. Here every right coset of H in G has same number of elements. That means H into 1 contains 2 elements, 1 minus 1. H into minus 1, H into I, H into minus I. All these contains same number. That means 2, only 2 elements. So in every case, every right coset contains same number of elements. And the number of right cosets of H. Here 4 right cosets are there. If you take distinct, they are 2. Anyhow, both are finite. So that is the meaning of the second line here. Now, let H into A, H into B, H into C and so on are right cosets of H in G. Just like H into 1, H into minus 1, H into I, H into minus I, like that. H into A, H into B, H into C and so on. They are the right cosets of H in G. Also, since H is equal to H into E, because E is the identity element, if you multiply any subgroup with identity element, we will get the same H. So H is equal to HE is the right coset of H in G. Then order of H is same as order of H into A is equal to order of H into B is equal to and so on is equal to M. That means if you consider this example here, right side, H is equal to 1 minus 1, right? How many elements are there? 2 elements are there. That means order of H is 2. Next one, H into 1, 2 elements. H into minus 1, 2 elements. Number of elements here. H into I, it also contains I minus I, 2 elements. Similarly, all the right cosets contain same number of elements. That is equal to M. M is nothing but order of the subgroup. 1 minus 1 is the subgroup. If you take the example, order of H is 2. Similarly, all the elements in the right cosets, number of elements in the right cosets is also same. Let the distinct number of right cosets of H in G is K. So different right cosets, 2 right cosets are there. Similarly here we can let distinct number of right cosets of H in G is K. This is another number. All these right cosets are distinct. Distinct means they are disjoint and they induce a partition on G. For example, if you take 1 minus 1, I minus I. These two are distinct, right? If you union them, 1 minus 1, I minus I. They form the group G, right? So then if we take disjoint subgroups, then all the union forms the group. So G is equal to H union, H into A union, H into B union and so on K times. Then order of G is equal to order of H plus order of H into A plus order of H into B plus and so on K times. What is order of G? Order of G is N. What is order of H and order of HA? All these are M. So N is equal to M plus M plus M and so on. How many times? K times. That implies N is equal to, if you take 2M, so 2M we will get 2M. M plus M 3 times if you take, you will get 3M. Similarly, if you take K times, you will get Km. N is equal to Km means M divides N. What is M here? M is the order of the subgroup. And what is N? Order of the group. That means order of H divides order of G. So the order of subgroup of a finite group divides the order of the group, which completes the proof of the theorem. Thank you.